Hello, everybody, and welcome to the panel discussion on AI, ML, and the intelligent edge. I'm Rahim Tafazolli from University of Surrey, 6G Innovation Center. I have with me prominent experts from mainly industry who can share their views and experience with us and for the first hour, and then for following half an hour, more or less, we'll have question and answer session. I'm pleased to introduce Chih-Lin from China Mobile Research Center, Alex Reznik, which is former chairman of ETSI MEC and Hewlett-Packard now, Mostafa, Essa from Vodafone Group, and Detlef, Nauck from British Telecom. Without too much ado, I would like to start with the first presentation from Alex Reznik. Over to you, Alex.
Okay.
All right. Well, thank you.
Okay.
Thank you very much, Rahim. And welcome everybody to the panel. Let's just go to the next slide from the.
Sure, no problem. No problem.
So,
okay. Thank you.
A brief kind of summary of some of the points that I'm going to try to hit on.
The speaker, now I'm the last speaker. Can you,
here, it's the right, as a communication industry, I think we're just beginning to grapple with AI and its role as we are deploying 5G. And I think, as you've probably heard already from many other people in this symposium, and you've seen somewhere, the expectation is that as we go to 6G, AI is going to be one of those cornerstones, enabling technologies that are going to be necessary to make the promise of, or the promises of 6G a reality, right? AI itself, though, I think to us, as to any other industry that is using it, brings both promises and challenges. And I think in situations like that, asking the right questions and kind of knowing what those right questions are is really important. So what I'm going to try and do in this brief introduction is to just do that, just try and ask a couple of questions with a focus on the edge, and hopefully initiate some discussion both for the panel and beyond the panel. And that kind of seemed appropriate for to do for a panel. So let's go to the next slide. Before we go on to the questions, I want to give everybody a brief introduction to ETSI MEC, who we are and what we do, in case you don't know. I've had the honor and the pleasure of chairing the standards organization for 4 years, and just a few months ago, I handed this over to a good friend and colleague of mine, Dario Sabella from Intel. ETSI MEC is the standards organization that has been leading standardization efforts for edge computing in the telco industry for about 6 or 7 years now. We coined the term MEC, which has since become used and abused and overused in some sense. But really what we focus on are 2 areas that I think are central to the aspects of, or to bringing edge computing into the telco space. One is the management of clouds in the telco environments, right? And the and the management of workloads in those telco clouds at the edge. And the other one is exposure of API or exposure of services that telcos can offer to applications at runtime through standardized APIs. We are a very, very strong organization. You can see when these slides were made, we had 112 members, and most importantly, spanning the kind of the spectrum of the players in the space, operators, sort of traditional communication technology vendors, but IT players and some of the key folks from the application development community. We do a lot of stuff on enablement, including a lot of stuff, a lot of open source support that's available on ETSI Forge that I don't want to go into now, but you're welcome to go and check it out and ask me some questions for a follow-up on that. Let's go on to the next slide so we can kind of get into the meat of this presentation. As I mentioned, AI is being viewed as a key technology enabler of 6G. Not something I'm trying to make as a controversial statement, not something that I claim to in any way to somehow be a unique proponent of, right? I think as we look across the literature, AI and the capabilities of AI to solve complex problems that are kind of scaling beyond the capability of our traditional signal processing optimization approaches is just being universally seen as one of those things that we're going to need to figure out a way to make work for us as we deploy 6G. A couple of papers on that if you want to look at, and it's just a couple of things I pulled up from a very quick search. There's a lot more, but Nokia published a paper, a corporate white paper on communications in the 6G era that kind of very heavily highlights the role of AI. University of Surrey's 5G-IC, which Rahim leads, has a strategic vision that really heavily highlights the role of AI. So I think there's a broad industry agreement looking out into 6G that AI is going to be an important player. And I think some of the folks on this panel are going to go into a bit more detail of why and how and specifically where the promises of AI are. If we go to the next slide, what I want to do is kind of take that and say, well, okay, what has AI done in other industries? Where are the successes in other industries and where are the challenges? The Economist, which is one of several favorite non-techie sources of mine, did a really kind of in-depth feature set on AI last summer, not too long ago, and with a focus on, you know, what's behind the hype. Is it really delivering on the promises of the hype, not for the communication industry, but actually in the industries where AI is being heavily applied. So a couple of key takeaways that I think are going to be important for us as we as an industry dive into AI. You can kind of see this picture in the middle, right? It is more complex than it looks. Average time allocated to machine learning project tasks, right, is fairly significant. The other very interesting thing that this picture highlights, especially for us, is when you look at the proportion that's actually spent on algorithm development, it is very, very small compared to, let's say, the way we're used to doing things as an industry. We've always been a very algorithm heavy and algorithm-driven industry in a good way, in a sense that we've always been innovation-driven, and yet here we're seeing that as companies are working with AI, they're spending most of their time on doing stuff with data, cleaning it, labeling it, augmenting it, aggregating it, finding it, right? Well, identifying it, which is not finding data necessarily, right? One thing this picture doesn't show, which I added to the left, is finding that data. There's a presumption in this particular study that the data is available. There's a number of separate articles that Economist has written on the availability of data. Where's that coming from? Well, when we look at AI today, it turns out that data determines performance much more than algorithm does. I pulled up a little snippet sort of on the right from TensorFlow docs that shows the code for a fully viable TensorFlow neural net model, including, I believe there's some training code in there, not meant to be read by you, right? But it's just an illustration that with the tooling and the availability of sort of well-known, used and tried out open source AI, ML libraries out there, it is really fairly easy to build a neural net that and then build a training program around it, right, as well as an inference program around it. Once you have, right, it really takes, and I've done it, it can take as few as a couple of dozen lines of Python code. That's not to say that it's going to be a great model, but it turns out that if you have sufficient amount of data, a good enough and a large enough model will be enough. The data, on the other hand, is critical, and it's becoming ever more critical, right? Same kind of in-depth study from The Economist. They show the cost of AI computing over time, and you can see over here, it's suddenly jumping up. The cost of actually implementing these algorithms has gone up. Where's this cost coming from? It's obviously not coming from this. This is the compute time that's needed to train ever more complex models. Well, of course, the compute time means the models are bigger, they're more complex, but it also means that they have to consume a lot more data. And so I think what we're saying is this problem of data and where is it going to come from is going to be very, very central for us in AI. And what does it impact? It impacts everything. I spent quite a bit of my time on kind of near-term projects and working with customers, right? Understanding the value chain is very important. Well, if data is so central, what does it do to value chain, right? If there's no data, then there's no such thing as an AI-based component of a 6G system. Standardization, is this something that we need to look at standardization? And then another interesting question that I think is keenly important right now for 6G, how does that impact research, right? This incredible need for data. Just think about where the data is going to come from. And if the algorithms are kind of standardized and well known, but the data is critical, and you think about the kind of papers that we're publishing now, the kind of emphasis that exists in research, will that change that emphasis as well? Let's go to the next slide, right? Let's kind of take that data and drive it to the edge. What does the edge do? And how is it important in the context of AI? So edge today drives the success of AI where it is being used. And so I think just to that extent, it's going to drive the success of 6G. There's lots of other reasons why edge is going to be increasingly important for 6G, but AI is as well. Edge is the source of a large amount of data, if not most of the data, right? It is also the target of much of AI decision-making. Those decisions get implemented at the edge. And thirdly, when you look at structure of how machine learning gets deployed today, especially when it's based on a lot of data, right? There is a reliance on limiting upstream traffic through kind of a first step inference at the edge, right? And a canonical example of this is facial recognition from surveillance cameras. There's a huge amount of video stream that comes off of a set of fairly high resolution surveillance cameras. If all you're doing is facial recognition, there's very little amount of data out of that you actually need. So you want to introduce a pre-processing step, right, to limit that. So that first inference step that's used to limit the load on both your network and your compute infrastructure in the cloud from that data. What does that inference mean? It basically says, well, I have a set of underlying problem assumptions, right? The context that comes from the edge, understanding of the data aspects that are irrelevant to my problem, right? And then we incorporate that together with training data to develop the inference model, but it allows us to reduce the amount of training data that we need because it simplifies the model or the complexity of the network that we're going to use for inference, right? And then we use the relevant data that we collect and set upstream. We use it for continuous final results and model improvements. And you can see where that context is really important, right? Once we've built it into the system, it becomes somewhat self-reinforcing because it's used to filter out which data is relevant and is sent upstream for model improvement. When we talk about these problem assumptions, what are they? Well, underlying problem assumptions, I've been calling it context, right? And if you kind of try and define context, these are the underlying problem assumptions, and this has been and will continue to be the strength of being at the edge. This is what makes a lot of things feasible, right? It allows us to deal with the data frugality. There's a different word which has pretty much the same definition, and it's bias, right? It's those implicit underlying assumptions that we use. Bias, however, when you call it bias, is well known to be the Achilles heel of AI. And so, again, back to our canonical problem of facial recognition, it's well known today that at least, and to this day, many facial recognition systems work best on white European male faces because they were trained on data sets that were very heavily skewed towards white European male faces. It's a problem that industry is very quickly addressing, but it took them a little while to realize what was going on, right? And so I'm not saying that in the communication industry, our bias will drive these kinds of societal issues, right? I will touch on them, but bias can impact just the performance of our algorithms in a very significant way, and so that's something to pay very careful attention to. Let's go to the next slide. So, to summarize, as I said, I don't have answers, and I think we're far enough out there that the need to raise the right questions and start thinking of them is important. So some very, very simple points that I just tried to make here. Data is going to be super, super important. It drives the success of AI, and therefore it's going to drive our success in 6G. And we need to start thinking about what the data is and where is it going to come from. And then we need to be careful when we look at the edge, which is, again, where a lot of the data is going to come from and where a lot of it is going to be used and where and what a lot of it actuates, right? We need to be super careful of this double of the two sides of the coin at the edge, the context and the bias. Same underlying thing, the implicit assumptions. If we use them right, we get context, we get the benefit of being at the edge, we make our systems work. If we get it wrong, what we get is bias, and we get all the hidden dangers which come with bias built into AI ML systems. So that's it. Let me stop here and hand it over to Mostafa.
Thank you, Alex. Thank you very much for these illustrated slides. Good morning, all. Good afternoon. In my slides, I'll try to integrate more about the idea of adding the AI to the telco. And I will give you some flavor about the use case that we already right now working in it, in the 5G, and some futuristic use case that we can develop soon with the 6G in this slide. So this is like the evolution of network intelligence, and I'll grab it here from the ETSI as well. Some definition about the centralized controls visualization for the telecom network, and how in the ETSI we try to adapt this evolution of the AI. First of all, I try to introduce myself. I go down to the slides. My name is Mostafa. Essa. I'm working for Vodafone as an AI and data analytics distinguished engineer. I'm also a BB and a board member academia, board advisor of some academia worldwide. I also work with the ITU and focus group that is working with the AI as well, and also at an ETSI in the ENI. Back again to the slides. You can see here from what ETSI was writing in the ETSI, how we evolve, how we have integrate the AI with the telco gradually year after year. And you can say from the beginning we have this kind of virtualization in order to have an enablement for the automatic action or the automatic tasks over the network. Then we have some mid-adaptive network, and then we have the fully or the final autonomous, which is right now we are trying to finalize in the ETSI, to finalize standard ETSI. And you can see from the next slide here what we are trying to do in Vodafone. For example, you can see here the step of autonomy is or the grades or the steps of autonomy that you can see. One of them was called the automation, and here like an illustration for this process. Which is, you can see automation for task 1, task 2, task 3, task 4. And if you add all these tasks or these automated tasks together in an integration ecosystem, you can finally have the autonomous function at the end. And you can see it here, as you can see here from the next slide. I try to give you an imagination about what we will try to do with an autonomous service operation center in the telco, which is a SOC. If we have some automated alarm compression tool, for example, which is automated tool, and we have another automating tool, it's called automating alarm clustering, for example, which is doing some AI or machine learning alarm clustering processes, as well as automated pattern recognition for the alarms or the events from the system, as well as the trouble ticket correlation or dependency and data mining. If we add all these separate automated tasks together, integrated together, we will have finally the autonomous SOC, which is the final or the ultimate goal for these steps of automation. And like a glimpse of what the IT guys was always working in the past And right now, we at the telco have evolved ourselves to work directly or hand-to-hand with an IT concepts and IT models. The old traditional way of programming was just you write a program, whatever in which code, and then you have some software inputs, and then you do the execution, and then you have an output. This was the traditional way. With the machine learning and AI, you train the model. You write the system, and you have an input and non-output. And you let the system or the algorithm try to find this kind of correlation to have a learning program at the next step. And then you let this learning program work automatically or autonomously to do some inferencing to have an expected output at the end. I will go directly to the use cases. And you can see here some, I will try to concentrate more on the radio access network part and some other part with some research for the spectrum. And you know, AI, we always use the AI, even in our personal life, to enhance our decision making. Sorry for that. By give us some insights that the machine learning model can give us some insights to allocate much better resources in our life, in personal life, and as well as in the business. So each resource in the network will be hit or be impacted in a good way if we imply the AI in the right way in it. So in this use case, which is called the geographical use cases or geolocation use cases for the radio access network part, you can see here like a landscape of the mobile network and how the AI can do some clustering models or some forecasting or prediction models to identify some problem. The first one on the left here and the first left quad is called the overlapping detection, where the AI can help the optimization engineer in the telco to find the overlap cells together. You know, in the telco, each and every base station have an exact or a designed or desired network coverage footprint. And if you do, and it's important to have some overlapping, but on the edge only. If this overlapping became much more than desired, it causes an interference and a lot of bad quality problems. That's why it's very, very important to identify the overlap cell for the 4G and 5G, and as well for the 6G as well, to rectify this point from the radio optimization point of view. The data hotspots, you can find which is where is the most important geographical hotspots or spots that your user heavily download and do a lot of streaming and gaming, as well as using the prediction, the traffic profiling clustering model and the machine learning, as well as for the throughput geolocation, you can classify as well in the clustering model the areas with the poor speed, and you can do a more deep detection or troubleshooting to find what is the main reason of this poor speeds, as well as for the call failure analysis. Machine learning is not only about the radio assistant, because I told you, but also we use it for the green concept in Vodafone. We are go green, so we will write always to try to optimize our backup system or the battery system on anything related to the power consumption, try to reduce it. So we implement some AI models to balance the battery at the same level with the discharging, to prolong the life of the battery. This is charging logic to do some efficiency during the discharge. You know, the batteries in the base station have a lot of strings for batteries. So it always, for example, when you have a drop or a power outage, you're always using the first string to do the discharging process to power on your base station during the blackout, and then it back again. So when you concentrate all your work on one string, it damages the battery, and as well as with the statistics, we found that we consume much more power. So if we distributed this discharging logic using the machine learning to identify which is the best string to use right now and when to stop and when to use another one, it improved our power consumption as well. For the entity function, which is related to the something like the two-factor authentication, it's something good to identify where the battery have been installed. So if someone stole the battery to use it in some other function rather than our base station, the battery will be blocked and will not be functioning well. Balancing the battery at extreme low level, as well as it is the same as discharging, but it improves efficiency of the power usage in each and every base station. And I will give you speed or a very quickly briefing about some other use cases that we use it. There is the machine learning inside the telco, inside Vodafone. We have the predictive maintenance use case. We have a study here and to convert all the alarm fixation process from reactive mode to have a proactive model. So we can predict the problem before it happens from some pattern or some sequential events. Using data mining and deep learning methodology, this tool aims to use the alarm history which in each and every site or base station to predict the future alarm. And it improved our operational KPIs over the last couple of years. On the lower one, which is called the NPS prediction use case, which is the Net Promoter Score, it is a score that we identify where our happy customer and where is our customer when they have some problem to complain about it. So right now, most of our call centers right now, or the chatbots that we have in Vodafone, have this kind of prediction. So once you have the call, you can predict if this user will be a promoter or will be a defector or a passive user, and then you can profile the chatbot or the agent to put him on some profiling or some specific way of handling. The PCR, the physical cell identity tool, which is we use it to optimize and plan the physical cell identifier for the 4G and the 5G. We use it in different places in Vodafone, and it was developed in Egypt. The lower one is called the multi-rad coordinated energy saving. And to give you like a small introduction about what this use case is working around, if you have the radio units right now in the base station, each and every radio units will cover some of the technology over spectrum or a bandwidth. But sometimes we use this kind of mixed configuration. So you have a one radio unit that can cover the 4G and the 3G, for example, or the 4G and the 5G as well, and the same radio unit with a sharing power capability. So if you want to do a power saving mode to close some of your resources at the low traffic time in your network, you have to shut down both of this technology, which is not very good for the customer point of view. So when you have this kind of multi-rad coordinate energy saving model, you are trying to manipulate or maneuver between the different clothing or shut down the different technologies on the same radio unit. And if you can see here from the real life results, you can see that we saved about 18 minutes of running on a battery rather than it would be shut down if we keep it with an old way of the energy saving feature. So the last one here, I will talk about the radio asset radio unit, which will be the spectrum monitoring model. And we have a published paper in IEEE GlobeCom in 2019 about this scientific research, which is turned to be a tool right now that they're using the AI to detect and predict the ducting abnormal phenomenon, which is something that happened to the spectrum that extend itself due to the high temperature and humidity without any planning or planned action, which is impact the other side with the interference, and sometimes it deteriorates the customer experience. So it is autonomously right now take a proper mitigation action for this when it find this ducting problem happen or about to be happen, it predicted, and then it takes some mitigation action, and then it restores it to the normal configuration once the ducting phenomena disappears, which is a normal phenomenon, by the way. Which is another one for the SOC. It is the SOC use case for the alarm compression pattern recognition, which is can identify what is the hidden pattern in the network, in the alarms on the network, as well as doing some clustering for the trouble-taking correlation and dependency to the perfect or the most suitable teams in the network. And this is one of our futuristic use case that we was talking about in Vodafone. We have some patent on it, which is called the cognitive hit on networks, or the cognitive hit nets. And we think that in the future, the fixed base station concept will not be the most suitable thing for the 5G, even not only for the 5G, but as well for the 6G. So you have to have this kind of mobile base station, like on drones or on the cars and so on. And if you have this kind of moving or mobile communication drones, for example, or base station, you have to control it, and you have to do some orchestration for these resources, which is right now a physical resource, but it's something that you have to manage it through the AI. So if we take this kind of distributed cell or drone cell, you have some information about it, the base station, and because all these cells will be backhauled over another 4G or 5G cells, and then you have the connected nodes. This is like the case of features, or the simplified features of that will be used in the AI model for managing or orchestrating this mobile movement or this mobile base station. And then you can control it from a centralized node, or even from a distributed node or a terminal node, and you can do some action like ranking, initiation, allocation, and waiting for this one. So this is like a small illustration. Sometimes you will need a cell with a higher coverage, which is already moving, and the other two neighbor cells, which is not good to propagate in this area. You have to close it, or you have to reduce the power of emission from emitted from this cell. And this is like some use case or something that we did in London. And you can see here this kind of red spots, which is a mobile base station, which is working over the fixed base station. And you can see here how the AI can allocate it, or can find this kind of quads to allocate where is the best or the nearest neighbor for the base fixed base station or mobile base station, and then it can adjust its own power and signaling parameters to not or to serve the customer with the most optimum thing without interfering with the other moving or the other fixed base station as well, which is you can see here from so backing into this one. You can see here how it's allocated from a geographical point of view, and how the machine learning at the back end do some a lot of action to optimize or to dynamically optimize this kind of distributed cell according to the surrounding neighborhood sound system. From here, I will stop talk, and I will hand over to my colleague Detlef for his next slide. And thank you very much.
Thank you, Mostafa. Hi, everyone. Detlef Nauck. I'm running the AI and data science research program at BT. My background is computer science with a focus on data science and machine learning. So I'm not a networks expert as such, but I want to give you a few thoughts around what does it mean to use AI for networks, and what sort of challenges do I see ahead in this space. Next slide, please. So the first thing that I notice when I speak to people from both fields is that there are quite different views about what are AI and networks, and what can AI do in the context of networks. AI experts think differently about AI than networks experts do, I believe. And when we look at how AI has developed over the last 10 years or so, and how it has been used, then you can see that AI is always used for a very kind of point solution. So even if it looks very impressive and complex, like image recognition or natural language understanding, it is always a kind of a very limited scope in terms of what this AI system is doing. The AI system also has no clue what it's doing. It's just doing pattern detection, pattern matching, pattern recognition. So it is not really intelligent, if you like to say it like this. And also AI experts tend to see a problem as a black box, and the data comes out of it, and then they know what the answer should be. And this is then used to impact on the black box again, if you think of it as controlling a device maybe. And kind of this is what is being attempted with autonomous cars. All the sensor data that you have is not understood as such, but it is used to control the car. And we have all seen the examples where this has limits. And this is also a good example to understand that data is not everything, because you need to understand the context you're operating in. You need to follow rules like traffic rules. And so this whole complex scenario cannot really be fully described by data. When we look on the network side, I feel that network experts expect too much of AI at the moment. And so the expectation seems to be that the data from the network somehow is collected somewhere, and AI system will use this to affect the network and optimize the way it behaves. And the current AI systems are not really in a position to do this. We have seen examples from like Alex and Mostafa mentioned, where we can develop point solutions, like proactive maintenance is a good one, for example, or kind of control of certain aspects in network devices. But until we get an appreciation of the complexity of the network and manage a network as an entity with a number of collaborating units, I think we have a few problems to solve. Can we go to the next slide, please? It was already mentioned, AI essentially depends on data, and networks give us lots of data, but unfortunately mostly of the wrong type. The successes of modern AI as we see today depends on machine learning, and this type of machine learning uses labeled data. And all the results that we have seen is either supervised learning, that means the machine learning system knows what the output should be and can adjust the parameters, or we have some sort of reinforcement learning where the system knows at least if the decision was good or bad. And this can achieve really amazing results, as we know from things like natural language processing, for example, or image recognition. And the reinforcement learning, for example, like AlphaGo is a good example, where the system learned to play by trying things out and playing against itself. And these things work really well. They also have flaws, as Alex pointed out, like bias is one of the obvious ones, because what these systems do is they detect patterns in data, and bias is essentially a pattern that you might not be aware of, but the machine learning algorithms are honed to detect patterns. So if there's bias in your data, it will find it and it will act on it. And this is a huge problem in many areas, in particular when people are affected, but you can also easily imagine it as an issue in technical systems when the decision has to be made. Should the system do X or Y? And if the decision is biased, then it might do the wrong thing. The network telemetry data that we get is typically unlabeled. So that means we have a lot of data where we don't know what the correct action should be. So it doesn't lend itself to be used in supervised machine learning that well. And there are obviously cases where that works, like, for example, proactive maintenance and other applications. But in the sense of reconfiguring network devices and redirecting traffic and reacting to traffic situations, we will encounter situations in networks that we haven't seen before, and where the data itself doesn't tell us what to do. So this thinking that everybody thinks of data means we shouldn't be looking down this one rabbit hole. We need to think also about other areas of AI that have been successful for a long time. And these are things like optimization, understanding the search space, and things like constraint satisfaction. And so kind of what you would now call classical AI, also based on data and machine learning, but with different focus. Next slide, please. And so just some thinking around what the future of networks can mean from the context of AI. And as I said, I'm not a network expert, but the way I understand network function virtualization means we're getting more freedom in networks, and more freedom means more complexity. And so from a kind of situation, we're moving from something that used to be kind of very rigid and constructed and engineered and tied down in order to manage the traffic flows more like a road network. We are going somewhere to an open space where people can move about as they wish, and customers who use functions in the network will kind of make their own paths through the network, and which means we are going to see usage patterns that will force us to react in ways that we haven't reacted before. And if we want to do this, and if we want to do automation in this space, we have to think further than just supervised learning in the type of AI that we're using today. And so we need to move from rules to concepts. So instead of saying you go down this path from A to B, it is more like you do something that makes sense in the context of the way the whole system operates. You do something that is to the benefit of the customer. You do this in a way that you don't interrupt other traffic, and you don't negatively impact on other components. And this is a different way of thinking about achieving a goal. And we need to move from labels to intents or to context, as it has been said before. So instead of expecting that the data that we have is a label, so that we know if we see this is what we have to do, we have to understand what is the context in which we operate and what is the intent of the operation, and then drive the automation through these sort of concepts. Next slide, please. So as a bit of a lookout, I'm trying to see what else is there in AI that might help to address this rather complex challenge, probably something that has never been done before. And so one area to mention is digital twins. And if we can't do supervised learning, if we don't have labeled data that can drive AI algorithms, then we may need a sandbox to run experiments in. So we may need to look at how do we get a proper simulation of a network with all its components that allows us to try out stuff. And that can mean that we, again, have to use AI methods and machine learning to build such a digital twin and tune it so it behaves like the real thing, where we can then try things out and learn without breaking things. There are new kind of concepts that are being discussed, like open-ended learning, which are combinations of reinforcement learning, generative adversarial networks, multi-agents, evolutionary algorithms. And this is to create challenges and data as these systems learn, and that allow goal switching. So the idea, you set out to learn something, as you do, you discover something that is easier to learn, and so you solve this problem, and it is useful in the wider kind of objective as well. And this is helps you to explore the search space. And this can also help us to create complex digital twins. We should look into collaborative multi-agent systems. That seems to me like a very good analogy of what a network is. It has multiple components who need to collaborate to achieve a common goal. And that means we need to move away from this kind of data-centric view to a goal-oriented view. What is it that we want the system to do? And we can look at areas that are a bit further afield, like collaborative robots and swarm intelligence, to understand how maybe these kind of complex systems can interact and what we can expect in terms of performance and automation in there. And then lastly, I'd like to mention autonomics. This is moving the whole idea of learning onto a different level of control. And this is understanding the dynamics of learning. How does learning actually work? And how do we control it? How do we make sure a system learns something that is useful and doesn't go off the path as it does that and doesn't start misbehaving? And how do we understand what happens when AIs interact in these kind of situations? All right, I think that's my last slide. Thank you very much. And I think probably I'm handing over to Chih-Lin now. Chih-Lin, you're on mute.
Okay, thank you. And I need to share the screen. So let me get. Okay, can everyone hear me?
Yeah, you're on.
Okay, thank you. Sorry, I had a little trouble connecting in the beginning, so, but I'm very happy that I had the benefit of listening to all the distinguished speakers first. So there's some of the material I can really go very fast. Great pleasure to be here. Thanks for the organizer and Rahim for the invitation. And I kind of titled this short presentation as From Wireless Big Data to Native Machine Learning and AI at the Edge. Okay, I think we have gone through very exciting transformation in the past decades of our network, and from the centralized RAN to collaborative to cloud RAN, virtualization, etc. In that process of transformation of the wireless network access architecture. At one point, I think as early as 2015, it has become very clear that there is going to be a turbocharged edge, both from the RAN restructuring and also some of the function repartitioning, especially core networks transformation into service-based architecture. And so that I think linked to one of the key theme of this deep dive session about the importance and the functionality, opportunity and challenges related to the network edge, I think from 5G and continue going on to 6G. Now, in parallel, just a couple years later than the other transformation, there was efforts started as early as 2014, exploring the opportunity of making use of the vast amount of wireless big data in our network to enhance or optimize various aspects of our network operations and performance. And I must say that it was unfortunately a missed opportunity in 3GPP, benefiting from this effort for its 5G standards work. Many of you know that the NWDA function was identified very early on for the core network 5G design. However, a complementary part of the proposal for the RAN data analytic RDA, which is composed of CODA and DODA, was not successful when it was shared and presented also around the phase 1 stage of the 5G standard effort. However, that does not stop our community from pursuing this great opportunity. So as you can see that over the past 6-7 years, there has been a lot of effort and fruit of labors in this direction, in the management plan, in the control plan, as well as exploration in the scheduling and all the way to the physical layer and the various aspects of function. I think our colleague in this session had highlighted some of these cases. And actually, we have seen great gains in many of these functions, especially in terms of maturity and commercially deployable capability. In the management plan, it has been, in some cases, a large-scale deployment already in the real network. But in the control plan, it's still more or less in the testing and trial stage. And the physical layer and the scheduling certainly is much more challenging because you look at the time resolution and also the resource resolution. This is much more dynamic and real time. So the control plan, I mean the scheduling and the physical layer capability are still more the research lab phase right now. And here are some of the samples of employing machine learning and AI capability in a real network. And I'm showing some of the cases here and also with the real trials and deployments in various provinces and operating companies. For example, this multi-red cellular energy saving capability has been deployed in 24 out of the 31 provinces in our network. And the anomaly detection has been deployed, and the load balancing has been deployed, and the cross-layer user experience optimization, various functions, has been either deployed in a small scale or actively being field trialed. And whereas the radio transmission related capability in scheduling domain or even the physical layer MCS optimization has been trialed, but not really in a deployment stage yet. Okay, in the meantime, even though, as I said, the 3GPP 5G standards effort has missed the golden opportunity, but many other organizations, alliances have been pursuing this direction. And for example, ITOT had a focus group, ML 5G, machine learning for 5G focus group. I think it started in 2017 and then was just concluded early this year and has basically developed a set of related specifications under ITOT SG13, but it's mostly at a high level framework in terms of data handling, in terms of the architecture framework and marketplace, as well as I think one most interesting one is the evaluating the intelligence level of future network. And so these are very interesting progress, even though I think a lot more in-depth technical work still needs to be done. And in the meantime, ORAN Alliance that was launched in 2018 has actually identified intelligence as one of the key objectives of the future access network, where particularly out of the 10 working groups, there are at least 3 working groups are specifically working on bringing in native machine learning and AI capability into the future radio access network. And when I say future, it includes the evolved 5G network as well. And specifically introduced a RAN intelligent controller in a hierarchical level fashion. There is the non-real-time RIC as well as the near real-time RIC. And let me show you, maybe here it's more clear. These 2 important controller, each operating in kind of a slightly different time frame. The non-real-time RIC would operate at like a second and above level, whereas the near real-time RIC would operate around more or less 100 millisecond level. And the 2 of them would couple together. One would perform more of offline training work and then providing the model to the near real-time rig for its near real-time inference use. Here are very important value that this hierarchical rig would bring from a practical business case use for service assurance work, needs, especially to address the various needs of diversified vertical industries, and to improve the network resource efficiency or energy efficiency, as well as for our RAN capability exposure to third party to provide value-added service opportunity. And very importantly, I think that our speakers have all talked about the data. Indeed, there are lots of, we did a lot of study, I think, to figure out what data we need for what kind of capability and where can we get it. And currently it's, the reality is that we do have a lot of data. Not all of the data are in the right shape, and also not all of data are actually readily available. More or less, we currently have access to the operation domain, business domain, and management domain data, but these data are really a small subset as far as our networks big data set are concerned. For example, the operation domain is accounting for less than 10%. And most of the data is what we call XDR data. The XDR data actually are including the signaling data on all the key interfaces. And these are not readily available, require extra effort. And more importantly, there are many other data that, as I'm highlighting here, they are traditionally not open, not, not readily available at all for open access. So there's a lot of work to do to figure out how to design the future network and make the data we need available in the right place at the right time. Okay, some examples of data-related work that Orion Lens has done. One example is in between the non-real-time rig and the near real-time rig. There are data that are needed for policy needs, that are also enhancement information, as well as machine learning model related data, and how to format them and how to provide a standardized and unified interface for this data to be collected and to be transmitted is an ongoing work. And there's a lot of progress that has been done, and I can't go into the details, but suffice to say, this design make use of some of the elements that's clearly defined in 3GPP, as well as some of the elements that's clearly defined in ITU. But even that is not sufficient. There are other data that are still being identified and defined. So bringing machine learning and AI capability into our network actually requires a lot more thoughts in terms of what kind of data, how to get it, and also how to minimize the burden of collecting them and transmitting them, and also what format that they should be unified, presented in a unified manner. And same thing with another example, which this is the OA interface, which is the OAM data model. Currently, the work involves both 3GPP compliant data model as well as IETF compliant data model, because both because of the different nature of this management data in the different interfaces. Also because some of it just simply is not visible and does not exist from CGPP's perspective. Well, overall, if you look at currently the machine learning AI related work, you can see that ITUT has been looking at overall framework level, but it's really very high level. While ETSI has quite a few programs looking at OSS and BSS layer architecture and interference design, interface design. Whereas 6GPP in SA5 has started working on the management more of the traditional OAM RAM capability. And of course, SA2 has been working on the core network, continuing enhancing based on the NWDA capability. Whereas in the RAM part, primarily ORAN is working on the non-real-time RIC and the near real-time RIC, both architecture and the key interfaces, as well as the data required and data formats. And we are right now in a very exciting time because going from 4G to 5G to 6G, we see an exciting, tremendous transformation of the network. In addition to previously, for the previous generations, the transformation primarily were in the air interface on the physical layer. But right now, we are at a stage where the ICT convergence is a kind of afterthought for 4G, but a starting point for 5G. And then going from 5G to 6G, the data technology or AI and machine learning capability is afterthought of 5G, meaning that we can probably expect it to be an aspect of 5G continuous enhancement, but it should be the starting point for 6G, as we seem to have the consensus already. So going into 6G, I think there are some of the clear consensus and as well as recognized challenges for this endeavor. I think I will just highlight the embedded control intelligence, which I think with the 2 RAN intelligent controller, we are already on its way. But in addition to that, the combination of the RICs as well as OAM functionality and the manual, which as the previous speaker has mentioned, the additional domain of the virtualization. This also is a complex domain where machine learning and AI would be, and also there is a very, I believe, a very intriguing phenomenon for us to observe from now to 6G, which is with the machine learning and AI capability, as well as our increasing open source communities participation, how a holistic impact of our traditional SDO on its way to deliver a 6G standards would be. I think it would be a very interesting thing to observe. And also, while we are pursuing this direction, the performance gains we get versus the computation complexity or power consumption, all the costs need to be taken into consideration. And in our field, we are used to talk about spectral efficiency, energy efficiency. I believe there is some measure of AI efficiency that needs to be considered as well. And then in addition, another point I'd like to make is definitely there is important work to figure out of a best balance of combination of AI and HI, meaning artificial intelligence plus human intelligence, okay? So that actually you can literally the data-driven, strictly data-driven approach versus our theoretical or knowledge-driven approach, which has been our primarily all of our solution that we have developed so far before AI and machine learning became a prominent contender. And then finally, while there's a lot of challenge that we need to resolve in terms of data, I believe the new generation of the network needs to have a built-in data design in mind, which would avoid the situation we are in currently, which is we have identified a lot of data that we need, which is not readily available at all in the current system. Okay, with that, thank you for your attention. Sorry for the connection problem.
Thank you very much, Chih-Lin and Detlef and Mostafa and Alex for fantastic presentations. So because of the time, I will shorten my presentation even more. And basically, I will mention very briefly the sort of research we are doing in 5GIC and 6GIC with regard to AI and all aspects of the network, which has generated lots of questions, which hopefully will be the basis of Q&A that we are gonna conduct. So next slide, please. So one important aspect of 5G is not just mobile broadband side, but it is the automation side of that, which is connecting machines, mass reliability, mass connectivity, reliability, low latency for connecting machines. And that most probably the decision needs to be made needs to be assisted by some form of AI system. Next, please. And also with full 5G, which all the size of this triangle is done with a network and network slicing, flexibility, open business platform, and et cetera, it will be too complex for human operators. And can AI help, not only on the core network side, but also on the radio access network, as Mostafa mentioned in his presentation. Next slide, please. This is an example. And because of the difficulty we had to find a common data format, so we need to apply AI at different layers, like an NFV layer or SDN layer, and as well as operation management layer, in order to make some intelligent decision before we give it to the orchestrator to make decision on the side of the whole network. And this is sort of research we are doing in 6GIC. Next slide, please. So these are my questions. And if we stop the presentation, everybody switches on their video, we try to go through these questions. And also we have a number of questions online from the audience that hopefully within the next 15 minutes, we can cover all of those. First of all, the current technology of AI, ML, would it be right to say the results they give, the decision they make, they give for the same set of data, the results are not repeatable. So the AI is not really stable. It doesn't always give you the same conclusion, even with the same set of data. Do you agree? on that?
I would disagree. So in that kind of wide scope, it's not correct. An AI system is simply a deterministic system, and same input produces same output. So there's nothing random or indeterminate within an AI system as such, unless you build it in for some reason. When we talk about repeatability or reproducibility, it's more like, can we build the same system again from the training data? And then you get randomness coming in by the selection of what is the training data, what is the test data. So you have to make sure that you do the selection in a way that it is reproducible. And you can, of course, have effects if you collect data and then you collect data again later, even if it is of the same distribution, that you don't get the same kind of performance out of the system. So you get these sort of effects. So reproducibility is an issue, but it should be manageable by the way you train these systems.
Well, so I think, Rahim, Detlef is the experts among us as the true computer scientist and the data scientist. We are probably, most of us are with communication background rather than really the data technology background. So definitely I agree with his opinion, because for me, it may be a naive observation, but I kind of feel that the so-called AI is basically a very different way for statistical analysis. It's basically statistics. So if your data sets are really coming from the same statistic ensemble, then it should be repeatable. But if it contains, different actual statistic hidden inside, then certainly the result will be different.
Okay.
Yeah.
So, okay, let me just ask Alex. Alex, you mentioned the biasness in the AI.
Yeah.
Yeah. So with regard to this question, where does the bias come from?
So I think it relates to the point that Chih-Lin is trying to make, right? I think we've seen so first of all, from a repeatability, right? Detlef is exactly right. These are deterministic systems. So if you always feed in the same data, right, and you run training for the same number of iterations to the same exact network, you will, on the same exact systems, you will always get the same exact result, right? You can ask kind of a more subtle question, which is what Chih-Lin was getting to, which is, as I start to alter my data a little bit, will the result of the system be completely unpredictable? And I think the experience that everybody has with these systems is if they're reasonably designed, right? Unless you do something completely silly, your results are fairly stable, right? Small changes in the input tend to result in small changes in the output. The one area where that's not true, and I can see some people being uncomfortable with it, if you start taking that neural network and you train it with a slightly different training set, and then you say, well, what is the value of each particular individual connection, right? How does each particular individual neuron work? You can start seeing unpredictability at those individual levels, but there's a point to be made there. You're not supposed to do that, right? You're supposed to look at this system as a estimation engine globally. So I think at that global view, we have the stability, we have the predictability. Bias, again, it's the two forms of bias. We want bias in some sense, right? Because that's what we're looking for. Those are the things that we're looking for. We just need to understand what are the biases to begin with in our data sets. We need to And if the biases that are there are unacceptable to us, then we need to understand that up front and go and look for different data sets, right?
Okay, okay. Well, let me go to Mostafa. Mostafa, you mentioned large areas that you're looking into use of AI ML, from network deployment all the way to quality of experience and network planning, even battery life checking, etc. So from your experience, what do you think about this use of AI? Do we have right AI or algorithm for networking? I think Detlef said AI and the networking are not aligned. So where are we with the AI algorithm so far?
I cannot agree more, but from my point of view and my experience during the last couple of years, we always start weak and then we came stronger with the days. So at the beginning, we built up a very, maybe a simple way of how to integrate the AI in one of the processes, for example, for a drop call prediction. You can just work with just a machine learning, a supervised machine learning, using a time series analysis, for example, to identify if these drop calls will happen in the same cell at the start. And then you can explore more in the features. And this was one of the comments that I want to add it after my colleagues and presentation. You can expect the same thing from the AI model. And as they said, if you only feed it with the same thing. So the right work for the scientist or the scientists in each and every space, not only in the network part, is to find what is the most appropriate data to use and to find the most right feature to identify before using it in the model. If you and me do or develop a machine learning model to serve, for example, the network, you maybe have your model much better than me because you study the data more better than me. I just take all everything and put it in the neural network, for example, and I'm expecting something at the end. But you sit with the experts, you knew what is the meaning of each and every feature, you know the correlation, you do a lot of correlation methods, and then you use it to train the model. So you did your homework, I didn't do it, and here you can find the different outputs from the machine learning from one point of view. For me, and back to your question again, I think that we right now, for me as in Vodafone, we have a very good matured use cases in the network, according to what we did during the studying of the feature and data. And that's why we evolved it.
Okay, very good. So that brings me to the next question, that at the moment, you can agree or disagree. AI or machine learning are black box. We don't know, we cannot explain why they do things. And when we come to network side, do we need a networking specific type of AI? That's what I'm saying. Do we need to go to gray box and we have open box to understand what it is, what it does?
Yes, black boxing, the AI is not always the right things to do, because sometimes you have a model that you already know, if you're an expert, you know, you're expecting and you even can test the model with an expert. You can see and check the result of the model with some of the experts in this field, and he can give a score for this model. So black boxing, everything is not the right, in my opinion, not the right terminology for the AI. If you're excluding the neural network and this kind of black boxing, by the way, it's this kind of hidden features that have been identified. But on the other side, not all the machine learning and not all the AI is black boxing, as well as in the network. And I will leave it to Detlef here because I broke his bill. Sorry for that.
Okay, let's go around the table, the virtual table. Detlef, over to you.
Yeah, I mean,
can you explain your AI?
You're absolutely right. Most AI systems are black boxes, especially the more complex ones like neural networks are always black boxes. And the kind of methods that we have to explain outputs are not really sufficient to produce explanations that can really be called explanations. So you can use these methods to understand impact of some of the features, and it helps in designing them and maybe detecting errors in these systems. But you can also question, where do we need explanations? We need them when it impacts people. But if we need to do automated decisions in whatever routing traffic, for example, maybe we don't need to have an explanation why packet A went this way and packet B went this way. What would be nice if we can debug these systems, if we can understand when something goes wrong, why did it go wrong? So explanation helps from this aspect. Typically, explainability means also that the models are less complex, and that means they use fewer resources, less time to train, less power to run. So it is desirable to have simpler models if we can get away with it. So this is a complex dimension, but I think you have to look into the specific use case, what is required, what model complexity do you need, and if you need interpretability or explainability, what should that look like? Yeah. Or is it simply enough to understand the model from a statistical point of view and know, okay, it's 99.999% doing what I wanted to do, and the other few percent I can manage.
Okay, I'm conscious of time because about 2 minutes we are going to be kicked out of the room. People, the questions online says that data sets are not available or widely available to do, especially data-driven deep learning techniques. Obviously, when you are Vodafone or you are BT or China Mobile, you have a huge amount of data available to you. So how can researchers, can you help researchers with the data sets? And would this data set, I think it was Detlef or Alex, I can't remember, they're not the same standard format. How can they be used? How can be made accessible anonymously, of course, and how can they be used by researchers in this area? Well, anybody would like to?
Well, I will try to first take a stab at that because actually for quite some time, I think we have consciously trying to make an effort. One of my slides had that title, Open Data Set. It was one of our conscious pursuit. Actually, when we launched the ORAN Alliance, we launched various working group and focus group. And one of the first focus group we wanted to launch is called Open Data Set Focus Group, because since ORAN Alliance has a lot of, currently close to 30 global operator support, it was expected that shouldn't be that difficult to collect, various data, contribution from a set of operators. And I think that we have quite a few colleagues that were interested to do it. But so far, we have not managed to convince our respective legal counsel in the company to let us do it. It's not an easy thing to do. However, on a smaller scale, I think we have been in the past 2 years, 3 years, launching various scales of so-called machine learning or AI context, where we have like a specifically defined problem with well-prepared, cleaned up, well-prepared specific data set for those problems. Okay. And usually provided to the academic community for contests. I think actually ITU is leading one of the global contexts which took place last year. There were probably, I don't remember exact number, but maybe not 100 different problems to solve, but in 20s or 30s different problems, all with respective data set provided by contributors. So programs like this are emerging. So it's so I would encourage more operators to join this kind of a program. Even though I have to say that from what I have seen, the available data set are still of limited varieties.
Okay.
But it's a starting point.
I've been told that we need to wrap up quickly. Thanks very much, Chih-Lin. I would like to thank you, all of you. We have lots of questions. I didn't even ask some of my questions. Hopefully, I wish that we had more time to go into this one for the benefit of the researchers in academia, as well as industry, to innovate more solutions on AI, ML side. I would like to take this opportunity and thank each of you individually. And I wish you all the best. Thank you.